Hi everyone. Today we'll be presenting a project called DARE-PM, which stands for Drift Aware Edge Predictive Maintenance. This system focuses on detecting BSR signals in vehicles, and the main idea is to make this detection faster, more efficient, and more reliable by using edge computing along with the drift aware logic. As shown here, the current system faces three major challenges. First, they continuously stream raw sensor data, which leads to very high bandwidth usage. Second is cloud-based processing introduces latency, which is around 100 milliseconds, which is not ideal for real-time systems. And third, it would be like machine learning models degrade over time when operating in such conditions. So the key issue is that while most systems can detect drift, they don't actually understand why the drift is happening. So we bring the concept of drift problem into this subject. In real world system, data keeps changing. For example, it changes due to speed or load, or it might be environmental shift, such as road conditions or the vehicle is hits some curbs or something like that. So environmental conditions such as that. The data distribution is changes over time. At the same time, sensor noise can also look like a drift, and real faults also appear as a drift. To address this issue, we use the existing methods like Adwin, which is used for detecting changes, but they treat all the changes as same. This leads to unnecessary uh, incorrect models update. So this is our system architecture. As shown in this diagram, our system is divided into two parts, the edge node and the cloud node. On the edge node, we process sensor data in real time, extract features, detect anomalies, and perform drift diagnosis. Then, instead of sending all those raw data, we only send compact event packets to the cloud. On the cloud side, the data is stored and visualized using the tool called InfluxDB and Grafana. This design helps reduce both latency and bandwidth usage significantly. For data pre-processing, we use multi-channel sensor data specifically for vibration and acoustic signals. The data is divided into two time windows, and from each window, we extract 14 features from both time and frequency domain. For the model, we use one class SVM, and this is trained only on normal data since fault data is rare. It outputs an anomaly score between 0 to 1, and we use a threshold to decide whether the signal is abnormal or not. To evaluate our system, we compare it against four baselines. These include cloud-only processing, static edge processing, Adwin-only drift detection, and our full DARE-PM system. We tested four different drift scenarios, including gradual changes, sudden shift, sensor noise, and combined effects. In total, we ran 48 experiments on the SWRU dataset and also tested our real traffic data using the IDMT dataset. Moving on, I would like to ask Nishant to explain from here onwards.
Thank you, Taran. Looking at the results from the CWRU dataset, we see some strong improvements. As you can see, we achieved 99.4% reduction in bandwidth usage and about 25 crores improvement in latency. The edge processing time is around 3.8 milliseconds, which is suitable for real-time applications. At the same time, the detection accuracy remains unchanged across all methods. So we are able to make the system much more efficient without sacrificing any performances at all. And moving on to the visualizations. So as you can see in the screen, these graphs show a comparison across different approaches. On the left, we see a bandwidth usage where DARE PM significantly reduces the so-called data transmission compared to the basic cloud-based methods. On the right, we see latency where edge-based processing performs much faster than the other things. And overall, these visualizations clearly show the efficiency gains from using an event-driven edge system. So this is the most important result of our project. In the admin-only approach, almost every window is detected as drift, leading to a false adaptation rate of about 49.87%. In contrast, the DARE-PM, the model that we implemented approaches a 0% false adaptation rate. So this is all because of our system doesn't just detect drift. It also understands the cause using multiple signals at the same time. So it filters out the noise and avoids unnecessary updates. And admin fires on every window because clip-to-clip variation in traffic recordings looks like drift. So the DARE PM's multi-signal diagnosis correctly identify these as a regular environmental variations. So this slide shows our system running in practice using a Grafana dashboard. We can see the real-time anomaly scores, thresholds, and the number of event counts. Each event packet is very small, around 232 bytes, which makes the system highly efficient. So this demonstrates that our system is not just theoretical, but actually implemented and working end to end as well. So to summarize, we built a drift-aware, edge-based system that significantly reduces bandwidth and latency while maintaining the accuracy as well. We also eliminated the false drift adaptations, which is a major improvement over the existing methods. And for future work, we plan to combine vibration and acoustic data into a single pipeline, and then deploy the system on a real embedded hardware. Thank you so much.